This is Walter Leite, and in this video, I will demonstrate how to use R and RStudio to perform a propensity score analysis with time-varying treatments. So this is part of chapter 9 of my book, Practical Propensity Score Methods Using R. So time-varying treatments is a situation where you have a longitudinal study with multiple opportunities for treatment. So at multiple waves, individuals have the opportunity to receive treatment. The treatment can be repeated, and there are multiple outcomes. So for this example, we'll use the National Longitudinal Survey of the Earth and to estimate the effect of self-employment on job satisfaction. So we use data for 10 years, and in these 10 measurement waves, there are 10 consecutive years. It's like every 2 years. For this period, at each measurement occasion, an individual may be self-employed. So there is a binary measurement of self-employed. And then there is also a measure of job satisfaction. Now, for these, we'll use inverse probability of treatment weighting, and the weights are a function of both the covariates, time-varying covariates, time-invariant covariates, as well as previous treatment history and previous outcomes. To facilitate the analysis, we will use a package called EPW. First thing we'll do is load the data, and then load the EPW package. Now, so the basic form of the weight is the inverse probability of treatment weight, where the numerator of the weight is 1 and the denominator is the probability of receiving the treatment at each occasion. The treatment, I mean, it's the probability of receiving the conditions that the individuals received over the time that has passed. So the denominator is actually a product of the probabilities for receiving each condition at each time point. Now, you need to estimate those probabilities, and the simplest way is with a logit model. So logistic regression, and that's what the EPW package runs for you. So in this code here, I'm using the function EPWTM, which is for time varying treatments. To estimate the probability of treatment at each time, I'm using logistic regression, which is defined for family binomial link equals logit. I'm declaring that exposure, which is treatment, self-employed. That's self-employed is the name of the variable. The time variable, which indicates time of treatment, is time recoded. I have sampling weights in this data set, so I'm declaring them as well as normal weight. And I'm not mentioning the numerator here because the default numerator is 1, given that this is an inverse probability of treatment weighting. The denominator is estimated with self-employment as a function of these main effects here plus these interactions. Okay, so there are some interactions here, such as degree and female and other interactions. I declare also what the ID is for each individual, and I'm estimating for a model for the entire data set with data that's called data long, which is data set in long format. This data set has as many rows as there are person by wave combinations. So here the data set has 91,500 observations, meaning that there are 9,150 participants measured at 10 times. Now, so once I run the estimation of the weights, I can do some diagnosis here using quantile to see, like I see here that there is a serious problem with extreme weights. So the maximum weight is a huge number. This happens with inverse probability treatment weighting because um, it's 1 over the product of the probabilities of treatment at each measurement location, which really inflates the weight. Um, and we'll solve that using stabilized weights. But for here, I just save this weight to the data set as shown here. Now, to solve the problem of extreme weights, we use stabilized weights where we replace the numerator, which in regular weight, the numerator is 1. Now we'll replace it by the probability of treatment given the previous history of treatment. Okay, so I'm running EPWTM again. And the only difference here is that now I have in the numerator is no longer 1. The numerator is the predicted probability of treatment given the number of times the individual received treatment before. So it's the history of treatment is used to estimate the probability in the numerator, and the history of treatment is also in the denominator. Okay, this has a consequence, which is because the history of treatment is included in both the numerator and denominator, this means that the weight is not going to remove bias due to history of treatment. Therefore, it's important to include the history of treatment in the outcome model too. So we'll add this variable here to the outcome model. So that's the only difference from the previous weight, which is the different numerator. Now, once we run this weight, we use quantile here to get a look at the distribution. And you can see now that the maximum weight is 22.4729. So the problem of extreme weight is gone. Now, I'm adding to the data set here. Now, there is a simpler form of stabilizing, which is not as effective as reducing extreme weights. The only advantage of it is that it would control for selection bias due to the history of treatment, because the history of treatment is actually not used to stabilize. So in this basic stabilized weight, I'm just using the proportion treated in the numerator. So I'm running again the same code as before. Now the difference, now that the numerator is 1 and that this 1 here is not the same as saying the numerator is 1 like the first weight. This is saying that the numerator is the intercept of a logistic regression without predictors, which is just the proportion treated. Okay, so once I run these, I get the basic stabilized weights, and you can see here that now the maximum weight is 1,192, which is not as extreme as the original raw weight, but it's not as small as the stabilized that uses the history of treatment in the numerator. Okay. Now I have 3 weights. This is called to plot them. I am going to plot the weight as a function of time and self-employment. Here, just plot the stabilized weight. this actually takes a while, so I'll stop. Um, so this does the plotting. Now the final weight, because I want to take into consideration the sampling weights. So my final weight is a product of the inverse probability of treatment weight, like the stabilized version of it, and the normalized weight from the longitudinal data set. So I get what my final weight is. Um, to evaluate covariate balance, I am using the Twang package and the function BAU-STAT within the Twang package, which gives me a covariate balance table. I'm declaring here my data, the names of the covariates that I'm evaluating balance. Jeez. From here, plot. These are the variables. Um, my final weight, the sampling weight, and I am looking at standardizing. So if I look at the summary of my balance results, I can see that I did okay. The maximum standardized effect size is 0.1252. In this case, like, so if I was using the what works cleanhouse from the US Department of Education standards, the worst possible baseline equivalence there is 0.25 standard deviation. So this is below that. Now we can compare that with the basic stabilized weights. The stabilized weights did a little bit worse than the stabilized weights. Now, I can proceed to estimate the treatment effect, and I use the stabilized weights. Now, the first thing I will do is to center the variable that is the number of previous treatments. And the reason to Gremlin center that is to preserve the interpretation of the average treatment effect in the model. So the coefficient of my self-employed variable can be interpreted as the average treatment effect. I also Gremlin centered the experience variable, which I will add in the model because it's an important covariate. Now, there are two models here that I will run to estimate the treatment effect. Both of them are marginal models. The first one, I'm going to use the survey package to run a weighted regression. So first I set the survey design with the SVY design package. IDs here is not individual ID. Well, in this case, it is individual ID. I mean, this IDs argument is designed to declare cluster IDs, but in this case, because it's longitudinal data, is like multiple observations clustered within individuals, so the ID is actually the individual ID. And then I declare what my final weights are and my data set. There's some commented code here that is if you want to use bootstrapping and if you want to estimate weighted means, but I will pass that just to the model. So I'm using survey SVY GLM, which is a function of the survey package, to estimate this weighted regression model here. General satisfaction as a function of self-employed, previous history of self-employment experience, time, and so time here, time recorded. So the original time variable was the year the data was collected. Now time recorded, just to show you. So the original time is the year that the data was collected. but I have to recode this to use it in the model. So the original time was from 1994 to 2012, and time recoded, it codes it as 0 to 9. Okay, so that helps with um, the intercept being interpreted as the the estimate of general satisfaction at time 0. Now, this is a linear model, so it's assuming that satisfaction is a linear function of time. Um, but I could add, time squared if I want the time cubed. And I'm also adding the interactions between self-employment, the history of self-employment experience, self-employment, and time. Um, and I obtain these results here, which shows that self-employment, individuals that are self-employed have higher um, satisfaction, job satisfaction. Um, the, however, there are some interactions. So this interaction between self-employment and experience indicates that, well, experience, the main effect of experience shows that satisfaction increases with experience, but the rate of increase is smaller for self-employed individuals than for not self-employed individuals, as indicated by this negative interaction. Okay. Same thing for time. There is increase in satisfaction with time, but that increase, the rate of increase is smaller for individuals that are self-employed. Now, the second way that I will estimate this model is with generalized estimating equations, which is also a marginal model. So this is, um, we use the library GEPAC to estimate the generalized estimating equation, estimate this model here. This is the model for the mean. It's the same model that I used before. I have to declare here family Gaussian, which is for the distribution of residuals, and my ID. And also I have to specify the time variable and a correlation structure for the relationship between multiple measurement waves. Here I'm specifying the AR1, which is autoregressive of first order. Um, Now, generalized estimating equation is robust to this choice, so it doesn't really matter that much. And I run this, and I obtain results that is slightly different, but in the same direction as with the weighted regression. So now the effect self-employment is a little bit smaller, but still significant. And we have some interactions. The interaction with experience was not quite statistically significant at alpha of 0.05, but the interaction between self-employment and time recorded was significant. So that's how to run um, the inverse probability treatment weighting with time varying treatments.